Hey, welcome to the end of our unit 5 today, our last bit of notes for this unit. We're going to take a look at how things or how molecules are able to cross through the membrane. So quick recap here, something we've already talked with, we've already worked with. The cell membrane is selectively permeable. Some things are able to just go right through the phospholipid bilayer. Other things are not. Sometimes molecules need energy to pass through the membrane, in which case that's known as active transport. Other molecules can do it without energy. And this is known as passive transport. So active transport requires energy. Passive transport can be done without. All right, let's take a look at these two. So some particles can pass right through the cell membrane. They can just diffuse right through, and we call that just regular old diffusion. Again, we've kind of already talked about that. In order to be able to squeeze through those phospholipids, you have to be small enough, so you have to be small. You have to be also be uncharged. So remember, these are almost like a magnetic force field. Anything that has a charge cannot pass through them. So generally, oftentimes we're talking about carbon dioxide or oxygen. These are small uncharged particles that are just able to freely move through the cell membrane. Other molecules, so hopefully recognizing this shape by now, is a glucose molecule, way too big to the squeeze through the phospholipid bilayer. So these molecules potentially need a carrier protein. Oops, I'm sorry, not carrier protein. I did this in class as well. This is a channel protein. So they can flow right through the membrane using a channel protein, kind of like a gate. All right, this next one, I'm going to draw two of them, but really it's going to be the same molecule. I'm just showing it change shape. So first of all, we have it pointed like this. And it can go back and forth from this shape to this shape. And this is known as a carrier protein. And a carrier protein has a couple of advantages over the channel protein. First of all, it's very specific. So again, so what you see happening here is the substrate goes into the enzyme can close around it, and the back end opens up then, and the molecule comes out. So it can be very specific. You see there, it's looking just for these big circles, wherever these big circles happen to be. But it also changes shape to allow for, and I'm going to finish that sentence in just a minute. We're going to come back and finish that in just a minute here. But yeah, these molecules go in, it closes on the back end, opens on the front end, and the molecules come out. Then it's going to go ahead and shift directions again, open to the outside, molecules come in, closes, opens to the backside, molecules go out. These are both forms of what we call facilitated, oops, sorry about that. Facilitated diffusion. So regular old diffusion passes right through the membrane from a high concentration to a low concentration. Proteins helping molecules get through the membrane is known as facilitated diffusion. So facilitate means to help. So facilitated diffusion means these particles are going through, but they're getting a little help from a protein to get through, whether it's a carrier protein or a channel protein. It's the facilitated diffusion. All right, next up, let's take a look at active transport. All right, so same concept here. We're passing through the membrane. Now, this is not going to be regular old diffusion. But it's going to go through a protein very similar to our channel protein or our carrier protein. But here's the difference. All right, so active transport takes energy, or needs energy. ATP is the energy molecule of the cell. Not that that's terribly important yet. We're going to talk a whole bunch about ATP in a couple chapters. You'll learn a lot more about it. For right now, though, hopefully you can recognize that the starburst is energy. So if you guys see that starburst, you know energy is being used. So that's the big way to know that you're working with active transport. You see energy being used. Now the home run message. Why? Why are we using energy? Why do we need to use energy here? Do you notice the difference between the particles on this side and this side? In active transport, we're moving particles from an area of low concentration to an area of high concentration. All of our passive transport, we're going from high concentration to low. That's a natural process. We talked about that a couple days ago when we did diffusion. So the reason why we need energy, the reason why we use energy in active transport is because we're moving particles from low concentration to high. We're moving it up the concentration gradient or against the concentration gradient. Again, that is not a natural process. This is a natural process. Going from high concentration to low, molecules tend to do that. You don't have to use any energy to force them in a direction they don't want to go. But over here, with active transport, you have to use energy to move these particles against the concentration gradient. All right, so now that we've covered that, let's come down here, finish this sentence down here. So a carrier protein not only is very, very specific, and channel proteins could be specific as well. Think of like a square peg in a round hole. But another big advantage, now that you've thought about the concentration gradient, is that these channel proteins oftentimes only work as long as you have a concentration gradient. So if all these particles flow into the cell, and then all of a sudden you have low concentration outside and high concentration inside, oftentimes a channel protein works both ways. It can just flow right back out of the cell. With a carrier protein, because he opens and closes, he allows for one-way movement. And that's a huge advantage. If we're bringing all these molecules into the cell, and then all of a sudden we don't have all these molecules, and they're inside the cell and not outside the cell, we don't want to just lose them all. So this molecule, it doesn't bring anything in, just stays closed. This protein does. It stays closed. These particles would stay on the inside. They wouldn't flow back out against the gradient, and we don't lose all the molecules we had to gain together. So that's a huge advantage that these carrier proteins provide. One-way movement, they're not going to escape once they get in there. You know, the channel protein, it all just depends. Maybe they all get inside and they just flow right back out. But one last little note here, I'm going to squeeze osmosis right in here. So osmosis is diffusion. Specifically, it's the diffusion of water. But I want to put it pretty close to a channel protein because generally the water does need a channel protein. We talked about it a few days ago. It's called an aquaporin. Now, the thing is that most cell membranes have hundreds, billions, maybe even of aquaporins. So it's not any kind of special protein. There's plenty of them all over the place. And so water can very freely move through the cell membrane. But it doesn't very freely move through the phospholipid bilayer. It doesn't very easily squeeze through those heads. And then, you know, because water has kind of a very strong partial charge, it really doesn't mix very well with those tails. So it usually uses a channel protein called an aquaporin, but it does kind of diffuse back and forth. That's osmosis, diffusion of water. One more note to add today. Proteins we just looked at are very good at bringing in small amounts of molecules. But for large quantities, So in order to consume or excrete, get rid of large quantities of molecules, cells use endocytosis and exocytosis. Hopefully the words kind of sound like what they do. Endocytosis brings particles into the cell. Exocytosis brings particles out of the cell. And so what happens, you have a whole bunch of large particles here. The cell doesn't want to take the time to bring them in one at a time through a protein. So just kind of surrounds them and engulfs them like that, puts them into what we call a vesicle. We'll get to that later. So going in this direction, the endocytosis. We're swallowing up those molecules, endocytosis. One last note to add. I'm hoping you guys can picture what exocytosis would look like. Just kind of be going in the opposite direction. You have a whole bunch of particles on the inside and you just kind of spit them out. Both endo and exocytosis are forms of active transport. It does take energy to do this. The cell has to move, has to surround the particles, and has to kind of pinch off the cell membrane there to grab those molecules. So it is an energy consuming particle process. It is active transport. All right, well, that finishes up our Unit 5 notes. Means we have a test coming up, so make sure you guys are kind of taking a look at looking at the material for the test. And I will see you again after the test. We start our new unit. Until then, see ya.